everyone, and welcome to day three of the AIMS Study Jam. And thank you all for joining on day three and keeping the consistency with the sessions. And today we will be following up from the day two and whatever we discussed in the day three, which is introduction to machine learning. We'll follow up with a little bit more advanced topics and today we have again Vibor who is going to be instructing and helping us better understand the machine learning advanced topics. And before I give the mic to Vibor, I wanted to share two things about today's session. The today's session is recorded and will be shared in our YouTube channel. Secondly, there is attendance which you have done in the past 2 days, I assume, and we'll be having day three attendance as well in the same form. And I'll be sharing the form again in the chat box so that you can fill out the form. So even if you missed any of the days, please do watch the recording and fill up the form to make sure you get the certificate of participation of the all 4 days, which is the final certificate. So yeah, with that, let's go on with the day three. Over to you, Vibhor.
Thanks, Ram. So can you unshare so that I can share and control?
If you should be having the access as well, right?
Okay.
Um,
No, I can't move the presentation forward or backward. Okay, thanks. Share now. Okay. Hi, guys. I hope you remember what we discussed last week. This week we'll go a little more into the theoretical part. Uh, it will correlate with whatever you have learned till now, but you'll need a little bit of maths and a little bit of visualization for this session. And our first topic will be regression, because how can we miss that? Most of this ML mathematics is based on the mathematics of line, and how, like, different distributions follow certain linear and non-linear patterns, right? And I hope most of you are familiar with regression. If not, I hope all of you are familiar with the equation of line and the whole concept. What regression is, basically, it maps the direction of the data. So what do I mean by direction of the data? You can see here in this plot, you have certain data points plotted on a 2D axis, and you have a line going straight through it that mimics the direction of the data. So obviously it doesn't represent each and every point in the distribution, but it gives you a general idea of, like, where the distribution is going. Like, and in this particular graph, you have to always remember, especially in regression, whatever you are plotting on the x-axis is the variable that you are trying to that you can control, and whatever is on the y-axis is the one that you are trying to control. So a very basic example would be, like, you're trying to just observe how quickly ice would melt on room temperature, and say you have uh, certain ways to control the room temperature. Say you have AC, you have heater, or maybe your house is centrally heated, and you have ways to change the temperature of your room. So you can change the temperature, and then you can observe how quickly the ice melts, and then you can, like, have a certain correlation between the temperature and the melting speed. So that kind of experiment, that's something like you might do for fun, or a kid might do. But you can also think of it as, like, you can also think of examples that would be applicable in commercial situations, in your jobs, or maybe something that you want to observe. Like, the easiest example is the COVID example. You can, based on, so obviously it would have much more parameters. It won't have a single parameter that you're manipulating, but you can still have certain correlations. And s- like, what do I mean by correlation? Okay, so it correlation is whether how the value that we want to observe response to the values that we can control or that we are observing. Okay, and it can be more than one also, but ultimately if there are more than one variables, like say, okay, if you want to predict weather, okay, and there can be multiple parameters like humidity in the air and like how windy it is, right? But each and every parameter will have a certain relation with the final outcome, which is like, is it rainy, is it is it a sunny day, and things like that. So if the value increases, or if you increase the value, and the value of your final output also increases, you'd say it has a positive correlation. And if the value if you increase your observation, or like control variable, with the value of your control variable, and if the value of the uh, variable that you want to observe decreases, you say it has a negative correlation. If you try to increase or decrease the value of the variable that you are trying to control, and it doesn't affect the final value at all, then you say it has zero correlation, right? In this particular graph, we can say it has a positive correlation, because as the value on the x-axis increases, the value of the y-axis also increases, right? So this is the basic concept of regression. And as you can see, here we have the equation of the line. It generally we represent the slope with m, but I have represented it with w, which I'll explain later why. Okay. uh, yeah, so this is the basic trend. So if you want to, like, if you have say 8 variables that you are observing, so you will have 8 2D plots, and each one will represent its relationship with the final point. And you can have, even though there are clusters of points, you can have a line drawn, and you'll have a general idea of what the value of y will be at, say, x equal to 2. There will be a small error, but but remember, in ml, it's mostly about the approximation, and it's all either approximated or probabilistic. You are not aiming for the ac- exact answer, right? You are just like, there will always be a small amount of error, and uh, like we can there are ways to decrease it, obviously, but we'll talk about them later. So this is the general idea. So talking about errors and going beyond lines, right? So not everything in what we observe will be linear, but there uh, just modify going 1 degree above, or just modifying it from a line equation to a polynomial equation, you can map different types of distributions as well. Here you can see this is a uh, polynomial curve, right? And you can have non-linear, a little more complicated relationships as well. But mostly if you have 2 lines or 3 lines, you can create all sorts of polynomial curves. Like, if you remember your maths, equation of 2 lines uh, can represent a lot of different curves, like a circle, right? There are modifications to the formula. It's You can check out the like geometric maths part, but yes, uh, everything that you can do with a single polynomial curve, you can also do with multiple sets of lines. So it's not like linear regression is redundant, but yes, if it will increase a little bit of your computation, that's a trade-off. And here also you'll see the values are not exact, they are approximated. if i had if say I had chosen a more complicated curve, it could have gone through all the points, and it could have satisfied all the conditions, right? But that would be a overfitted model. I think we discussed overfitting and underfitting last time. So if this this is this is an ideal curve. If we had tried to look for a curve that would go through most of the points, it would have been a overfitted one. And the problem with overfitting is that it mostly works for the data that you have, but it's very bad at predicting trends that it has never seen before, and sort of like mugging up the answer, right? So that's not what we want. So more complicated curves are not always the right answer. And talking about error, so you can see we calculate the difference from our predicted from the value on the line to the actual data point, and this particular difference is called residual. So we have a residual for this point, for this point, and for this point, for all the points basically. And then what we do, we uh, take all the residuals and sum it, and that is basically our error. So for error there are multiple formulas. You can simply add it. There is a mean square where you uh, like first subtract it and then take a square of the final value. And then there is root means root uh, RMSE, which is root mean squared. So like the formula keeps getting complicated, and it works for different situations, just like you'd use average and geometric average and harmonic mean, right? So similarly there are different variations and different complications, but but all these value will give you a general trend of where the error is moving, uh, whether you use RMSE or MSE, right? It would give you a general idea of where the error is moving. But in certain situations, certain error calculation formulas would do better, and that is why you'd see, if you do follow certain research papers, you would see that people sometimes come up with new or modified error calculation functions to boost their whatever like error calculation, or whatever probability that they have of accuracy, to improve that. uh, Calculating the error is the main part, because once you have a reference point, you can like adjust the slope of the line, say, or do certain modifications and try to reduce the error, or get get the error to as minimum as possible. So like simple base maths that you might have gone through during your school or college, right? Now let's take it a little uh, forward and talk about regression versus classification. The mathematics remains the same, as you can see here in this image. The only difference is the way we are using that maths. So here, so on right hand side, you can see there are different data points, and what we are trying to do is uh, predict the general trend of where the data points are moving. This can be practical in scenarios like predicting the stock market, which is a very difficult thing to do. But if you look at all the big companies, they have analysts, and they have certain mathematicians who are trying to like who try to give a mathematical analysis of how the market might move, right? And the second way to do it is that you say you have different data points and you want to separate them into groups, and say you have five different groups, or based on how well they did an exam or something like that. Like how or there can be like people from different ethnicities or something like that, and you're trying to predict based on certain data points, or based on certain uh, behavioral patterns, uh, who they are, or like what they might prefer. Because ultimately in a corporate scenario, you'll get a project where you have to predict about your end user, so that the company can uh, make certain judgments, give them recommend them certain products, things like that, right? So in the left hand side example, what we are trying to do is we are trying to separate the data points based on a curve, right? it's again using a polynomial equation, but it, instead of mapping the whole data point, it's trying to find uh, similar data points and like groups of data points, right? So in there are a lot of algorithms that can work for classification, and there are algorithms that work for regression. But if you go through any package like sklearn, you'll find for every algorithm that we are going to discuss next, there is a classification counterpart, and there is a regression counterpart. Okay. And I would recommend you to go through the source code or the documentation and try to understand how they are using the same uh, algorithm for two completely different tasks. But this, if you remember this image, you'd be good, because this represents how the same maths can be used for two different things, right? Okay, yeah. So next we'll talk about SVMs. SVM stands for support vector machines, right? And it is, again, it is the equation of the line, but it has a small twist. So here what you're seeing is a 2D plane, but how SVM works are that it would take your data and it would project it into a higher dimension. So say you have a data point, you have a control variable, right, and you have a independent variable, which you like a dependent, like you have a x variable that you can control, and then you have a y that you are trying to predict. Now you can't find a pattern in the 2D plane. So what you do is you project it into the 3D plane and see if there you can find a difference. So say there are data points form two concentric circles, right? You can't separate it through a simple linear equation. But if you project it into a 3D plane, they might look like two different parts of a cone, if you can try to imagine that, right? And there you can separate it through a plane, because in a 3D environment, a line becomes a plane. And that is why you see here you have a hyperplane written, because on a, if you go beyond 3D, a plane becomes a is called a hyperplane. You can have a fourth dimension, fifth dimension, sixth dimension, and generally it's very difficult for humans to comprehend beyond four. If you know 3D, right? Length, width, height. And if you add time as a new variable, you can imagine a fourth dimension. But going beyond that, it's very difficult to imagine it. But say 8 dimensions or 10 dimensions, but mathematically you can still do it on paper, right? And you can obviously convert all your data points and you can project them into a four-dimensional plane and a fifth-dimensional plane, and there you can try to separate it through a hyperplane. So again, we are using a simple line equation, but we are, instead of like going for polynomial equations within the 2D plane, what we are doing is we are taking the data to a higher dimensional plane, and there we are trying to separate it through like a higher dimensional version of equation of a line. And what are these margins? This is basically that whatever distribution you have should have a minimum gap between them. So there, this dotted line, this is what you call a soft margin. So all the data points should be on this side for them to be classified as blue, and on the lower side to be classified as green. But there are there are situations where you might never find a ideal solution, right? So what we do, and there are certain situations where you want a very high accuracy. So what the margin does is it ensures that there is a certain gap between the two groups, so you have a certain confidence that okay, these two groups are definitely different. But it is a soft margin, so there is a certain amount of error it's willing to except if the data points don't adhere to this margin. That is why, like, it's not implement followed strictly. That is why it's called a soft margin. And once you are able to find that particular dimension and that particular hyperplane, you can get it back. You can tone it down to, like, uh, tone it back to a 2D dimension, or like, there are certain kernels that you can choose. There's like, kernel is nothing but a mathematical function that you are selecting for this whole process of converting it to, like, higher dimension, and then getting it back from higher dimension to 2D dimension, right? And that way you'll have certain support vectors, or basically certain features that you can use to, like, that would uh, that you can use against new data points to classify them into certain groups. And again, this is how you are using the equation of a line for classification. So this SVM, right here, the example we are using for uh, classification. We can use the same algorithm for regression as well. uh, okay, but for most of the examples online, you'll find that SVM is used for classification only. There are certain packages that do allow you to use it for regression though. Okay, so again, same equation of line, but we change like, we just change the dimension. What are the drawbacks? Okay, I've told you the advantage. The advantage is that, like, you can find, you can take the same data point to, and you can use the same equation of the line and work around it, right? But the disadvantage is that as you project it to higher dimensions, you are increasing the number of data points. You are adding more and more information to those data points. So as you go higher and higher, your data set will keep increasing in size, because you are adding more information to it. So it will suffer from what we call a curse of dimensionality. So what is the curse of dimensionality? It's basically, the higher you go in dimensions, the larger your data set will become, and the more difficult it will be to process that data set. And you'll hit certain computational restrictions, you'll hit certain time restrictions, and this particular method will become infeasible. Unfeasible, basically. Yeah. So that is the drawback. Okay. There is another algorithm that you can use. Again, this decision trees and random forest, random forest can be used for regression as well. In sklearn there is a certain implementation for it, but it's mostly used for classification. And this is a random forest is a very popular alternative to SVMs, because it doesn't suffer from curse of dimensionality. Okay, so before you understand random forest, you'll have to understand decision tree. What is a decision tree? It's a very simple concept. If on a basic level, you'll find that it looks like a if else statement, right? So here in this example, we are trying to categorize people under certain standards of health, right? And we have certain parameters, say whether the age is above 30 or not, and whether their diet is proper or not, and based on that we are trying to judge whether they are living a healthy lifestyle or not, according to medical standards, right? And this is not like, this is a very toned down example. It just looks whether you are trying to, whether you eat junk food or not, and whether you exercise or not, right? But why is it different from the if else statement that we are discussing? It's different because it learns the conditions. So you are not giving it the condition whether, so this 30, and whether it selected pizza and morning exercise. All this was not selected by you, it was selected by the algorithm from all the data that you gave it. So say you gave it a data set with all the habits, right? And from there it selected certain features. Okay, so it say it had all the data that, like whether a person eats burger or not, whether a person eats pasta or not, but it decided that pizza is the most unhealthy food out there, and if someone eats a lot of pizza, then he is definitely unhealthy. Doesn't matter if he eats a lot of burger or pasta as well or not. So that's up to the algorithm and up to your data set and how, like, your training parameters. But this is what it came up with ultimately. Now, how it's making that decision? There are two popular methods. One is entropy and one is the Gini index. So, entropy, I guess you might have read about it somewhere, but but a simple explanation is that entropy is the measure of disorder. So, what we want is for the what we want is the feature with the minimum amount of disorder. So you might feel, okay, why, what is disorder, okay, what is chaos, why we are talking in this term, because it is initially a term that derived from chemistry, but the significance is similar. So uh, w- if I select, say, if it judges, if I select this particular feature, w- how certain I am about my next predictions, right? It tries to increase the certainty of certain events. That's how so it goes for so it goes in that direction, right? And you can see the formula, it it's based on probability, like how many what's the probability of our test case passing and what's the probability of a test case failing, and there are log functions to normalize the results, right, so that they don't go haywire. Gini index is the exact opposite. It looks to minimize the what it does is it minimizes the chances of us misclassifying it. So one is looking to maximize certainty and one is looking to minimize the uncertainty, like they're complementary, right? But again, uh, in certain situations certain approaches might work better. So in certain situations you are aiming to maximize the accuracy, and in certain situations you are aiming to decrease the amount of uncertainty, and this you can relate to the concept of precision and recall, right? So what is precision and what is recall? So a basic rundown is that uh, you plot the actual answers, okay, whether it's true or false, and you plot whether you were able to successfully predict it or not, right? So now uh, you have a four you have four data points, right? So recall is basically uh, s- uh, you can relate it to Gini index. It tries to minimize the unseen, and precision aims to increase the overlap between what you are predicting and what the actual value is. This is like a very basic definition. You can go ahead and like read more about the mathematics. It's a very popular interview question. They'll go into specificity and ROI curves and everything. The maths is not that complicated, so I would recommend you go into it. But for the purpose of this particular example, all you need to understand is that they are counterparts, and based on certain situation you might prefer entropy over Gini, right? And we have a question as well. So attendance related questions. Okay, Right. So this is a basic decision tree. Now, random forest. So the name is almost poetic, right? Because here you have a single tree, here you have multiple trees. So the algorithm is called a forest. Why a random forest? For that, you need to understand the concept of bagging and boosting, right? So just a minute. Okay, yeah, sorry for the delay. Yeah, so in bagging, you have two concepts, right? One is of sampling and the other one is of voting. So what you are doing is you are training multiple decision trees based on random sampling. Now how you are doing that sampling? In random forest, you are sampling the rows and the columns. So we sometimes refer to these columns as features. Okay, so you're not just sampling the data points like you're not just sampling the data points, you are also sampling what type of data points you want to take. So say you have let's take the house example. I think I took the house example last time as well. So say you have the area of the house, when it was built, right? And how many facilities it has within 2 kilometers, all these data points, right? And you're trying to fit a random forest. So what the random forest algorithm will do is, say it has eight features, right? And it has the information for 1,000 houses. So it will randomly select 4 or 5 features. That is something that you will decide how many data points randomly it should select, right? Say you select 5 data points at a given time. It sorry, 5 features at a given time. It will select 5 features, and then it will select, say out of 1,000 it will select 200 or 300 of those values or rows, right? Then it will train a decision tree. Then it will again randomly select certain of columns and rows. So here we are sampling with replacement. So it's not like if you have selected something once, you can't select it again. Okay, so it does that multiple times and it comes up with, say, 8 decision trees or 20 decision trees or possibly 100 decision trees. Okay, now that you have these 100 decision trees, each and every decision tree will make its prediction, and it will do a major voting, and whoever has the maximum number of votes, like whatever result has the maximum number of votes, would be selected. Say we have all this house data, and what we want to predict is whether we should move in or not. Like you are trying to select a house for yourself, right? So the ultimately the answer would be yes or no. That is your why, right? And say in random forest there are you have trained 100 decision trees, and 70 of those decision trees say that you should move in. Then you would select it as a good property and you would move in. Obviously you can or cannot train a random forest and take decisions that way, or you can go with your gut feeling. But it's just an example to show how a real estate company might use ML to decide whether they want to, like, buy a property and then try to resell it, right? So it would make much more sense in a commercial situation where you have a lot of say factors to decide upon, and you don't want to leave it to a single person's decision, because, like, obviously buying a house is a big investment even for a real estate company. So, and obviously it's just like an example of a house. You can obviously come up with many more examples where you'd want uh, certain decision making capabilities based on previous data, right? So this is the other thing is boosting, which again these two are ensembling methods. What is ensembling? Basically, you take a certain algorithm and you train multiple models, right? You can have different algorithms as well. You can have a mix and match, and then you try to use them for your prediction. The way you use them defines what type of technique you are using. Right now what we discussed here was bagging. The counterpart is boosting, where you basically cascade the algorithm. So the output of the first algorithm will go as the input to the second algorithm, and it would work sequentially. And obviously you can have different connections. It can have majority voting as well. And apart from cascading, you can also feed the output of those models to for voting as well. Like there are multiple ways you can cascade it and use the output. That is one. And then in bagging also there is a variation where you only randomly select, where you only sample the rows, not the columns. So random forest is unique in that way because it samples columns as well. But mostly when you talk about bagging, there is a concept called bootstrapping, where you only randomly select rows with the replacement. Here, you whatever you are doing is with replacement, which means you are not excluding those data points from further computation. Okay. Okay, one more concept that within random forest and decision trees that I want to discuss is the pruning part. So what is pruning? Pruning is nothing but limiting the uh, depth of your decision tree and eliminating certain leaf nodes. So this is something that you might call, the last layer is something that you might call a leaf node. And this is like completely uh, symmetric, but you can it might happen that this tree stops here, and for this branch there are more child branches, right? So it can be uneven as well. But in all these cases what we want to do is, one, define a maximum depth for the tree, and two, eliminate certain leaf nodes or the endpoint nodes that do not contribute much to the final prediction. So this we so this process is called pruning, where you eliminate redundancy, right? And this like again this helps in reducing the computation, because you don't want, if you have say 1,000 features, you don't want it to go endlessly in a decision loop, right? You want it to uh, make its decision within 10, uh, within a depth of 10. Say okay, judge these 10, judge like create 10 conditions at max to reach the answer. You can reach it in 5, you can reach it in 8, but at max I want you to utilize 10 features to come up with the answer. uh, that is another way of limiting the size of the model, and obviously it increases the speed. And you might think that it decreases the accuracy, but it uh, what it does is it forces the algorithm to choose the most important features. So out of those 1,000 features, which 10 features are the ones that contribute the most to the prediction, right? Because not every data point will be as important as the other data point. So that way you can like judge which feature is important and not or not. And uh, training a decision tree is a very like it's like a strict, but it's one of it has like if you read certain research papers, it is one of the common tricks to select important features. There are obviously other algorithms as well, uh, but this is the most practical and the fastest way to come up with the important features that you want. And why is it important to come up with the important features? Because again, you would be working on a big data set, like millions and millions of rows, and hundreds and thousands of columns, and you wouldn't want to go through all of them, or you wouldn't want to create a algorithm that goes through all of them, because you're trying to minimize the time and computation it takes to reach the right answer. And the final answer is, as I said, is either approximated or it is a probability. So if even if you lose 0.5% of predictive power or 1% of predictive power, but you can make it, let's say, 3 times faster, you might want to trade uh, for that speed, right? So this is why feature selection is important, and this is why decision trees are very good at selecting those features, right? You can obviously, there are a lot of papers, there are a lot of complicated methods to do it as well, but I find that this is the most practical way to do it. Okay, neural nets, the the most popular topic, so to say, right? And obviously, like I think most of you would be waiting for this, so let's go into it. So I hope most of you have seen such a structure. uh, Even if you're like following AI, if you're doing anything, there are a lot of articles that just throw this diagram or a similar looking diagram at you without going much into the mathematics. But this is like the bare minimum of a neural network. This is the input node, this is the output, which is basically the decision. You can have anything as an input, like from our previous example, you can have all the information of a house as input, and output can be the price of that house, not just yes or no, like I said, classification and regression. So if you are talking about the housing industry, you can select whether the property is good or not, and you can even select the approximate price, current market price of the property. This is the hidden layer. What is the hidden layer? These are the features that it comes up with, intermediate features. Like for example, instead we have for housing data, we have length of the house and breadth of the house. Maybe there is one particular node that says, okay, I can combine this into and calculate the area and then use that for the output. So here again, you are just giving it the initial set of features. What it's doing is it's coming up with its own feature set and then using that to make the decision, right? And this is just one hidden layer. You can have multiple hidden layer, and each and every hidden layer added would make the feature more and more and more complicated. So one very basic example is that if you do it for the image, say instead of features, this is pixels, right? And instead of two, you have, say, 1,000 pixels, right? It's like 100 cross uh, not 100. Say it's a 100 cross 100 image, right? And we have 10,000 pixels, right? So you would have 10,000 input nodes, and then you would have convolution operations, because as you remember, last time we discussed it in OpenCV section. uh, we, we use a convolution operation on images when we train when we train a neural network. And if you remember the notebook as well, the Colab notebook that I shared with you, it used a conv2D function. So that is a mathematical convolution operation that is being applied on the image, which is basically the hidden layer, right? So it applies the convolution operation on the image, and whatever output is there, that is considered as the hidden layer. And then you can do it again and again and again to reach certain uh, answers, like whether a dog is present in the image or not, right? So this node can be a convolution operation, or it can be equation of a line as well. And why, that is why I used W there in starting, because instead of slope it can also represent a matrix calculation. Okay, so for all practical reasons, what we use b equal to 0 initially, which is the bias. We generally keep it as 0. So the equation becomes W into X. Both are matrices. Even if it is not an image, you have say 10 or 50 features going in. They will be converted to a 1 cross 10 matrix, and they will be used for calculations with the weights inside the hidden layer. So the value of the hidden layer is basically a single weight. So like in this image, the size of the weight is 1 cross 4, and the size of the input is 1 cross 2. Okay, this is like not a ideal example for uh, matrix calculation. This is like you are projecting the values to different nodes, and internally it's using an equation. But uh, it would make more sense through this diagram, where you have multiple inputs and all these inputs are used for calculation, right? So it's just it becomes a function of the sum of those values. So ultimately what we are using is multiple equations of lines, and we sum it and we use that. And you can see here is a f function symbol, right? And we feed that to a function, and that gives us our output. What is that function? That is the activation function. So why do we need an activation function? We need an activation function to make certain judgments whether this particular feature is important or not, and if it is important, then how important, right? And whether it should be sent forward for next calculation or not. Okay, so now we have two parts. One is this calculation related to the equation of line, and second is the activation function. And this happens at each and every node. So each and every node will be performing this particular calculation. So again, using multiple equations of line. And it gets more complicated. It gets into polynomial equations as well if you study about RNNs. But for that, I'll point you to a better resource. We are not going to cover RNNs right now because that would be a complete overload. So this is the basics of how a feed forward neural network works. Why a feed forward? Because it's only calculating in the forward direction. That also means that we have certain calculations that go in backward direction, which I'll discuss later, which is called backward propagation. Okay, but you should be familiar with this concept, right? And what this activation function is. Just remember this equation and this process, and I'll explain activation function. So these are the four most popular activation functions, right? You can find it anywhere online. But what's the purpose of these functions? The purpose of this function is to judge whether a given feature is important or not, and if it is important, then how important. Okay, you have a sigmoid function, right? And I think I've explained this last time as well when we are going through the notebook. But what we want is this slope to be very small, so that it can instantly fall in one of the regions, either 0 or 1. Now having a 0 or 1 can help you make decisions, yes or no decisions. And that is why uh, last time I recommended that you use the sigmoid function in your output layer, so that it would give you a distinct 0 or 1. instead of a number, and you that would help you in your classification processes, or like getting the final answer, whether it is 1 or 2 or 3. Like last time we did an example for MNIST, right? So this is the reason why we selected sigmoid. This is there's a linear function as well, but ReLU, and there's a variation called leaky ReLU where it has a very small value in the negative axis as well. But ReLU and leaky ReLU the are quite popular, and when to use ReLU and when to use leaky ReLU, it's again up for debate. It depends on the situation, and you'll have to experiment a bit, but the concept is same. If it is below certain value, don't send it, and if it is above a certain value, send whatever that value is. So that is why it is used for internal computations, because in internal computations, if you just do 0 or 1, then the next hidden layer will become redundant. You get the point, right? Like, because if you are sending zeros and ones again, and the next layer is trying to use this particular equation, so it would directly start eliminating your nodes in the second hidden layer, right? And the second hidden layer would become redundant. So that is why leaky ReLU is popular. A second popular function is tanh, where it gives the 1, 0, and -1. So this gives us three options, and it why is it better than sigmoid? Because you can have a yes, you can have a maybe, and you can have a no. And you can also use tanh as a gating operator. Like, there are a lot of things you can do with these three values, right? So again, as I said, it depends on the situation, whether you want uh, whether you want a distinct 0 or 1, or whether you want to project those values as it is. Say maybe in case of images, you want the exact pixel value or whatever it is to go forward, instead of converting it to uh, an absolute 0 or 1, right? Now, the output layer will have something called the loss function. This is something that I discussed with linear regression as well, and something that applies to all the algorithms, to SVMs, to to random forests, uh, like the in like calculate like while calculating the accuracy in classification problems. As I said, we mostly go for precision and recall, right? And then there is something called F1 score that we use for that combines precision and recall. And no matter what the problem is, if it is a classification problem, precision, recall, and F1 score are the most popular ones. And if it is a regression problem, MSE, RMSE are the most popular one, right? But with neural networks, you can have certain more complicated functions. Like MSE is still present, right? You can see the formula. It's just the actual value minus what you predicted to squared and summed over next values. So that will give you the uh, intensity of the error, right? But for certain cases, you can have uh, more complicated formulas, like cross entropy, or you can have logarithmic losses and everything, right? These are just two examples in front of you, but this is what a loss function is. And just like any other algorithm, the last node that we have here will execute the loss function. It will compare its output to the that it got from, say, sigmoid function or whatever, to the output, to the actual value, and then it will try to calculate how far off it is from the actual value. And what will it do with that? In our previous examples, previous algorithms, what I said was, okay, you can try to adjust the line, So you can again change the input parameters to see if you can fit it better. But with neural networks, what it does is it takes that particular error and it starts calculating uh, how much it should adjust to get to the right answer. So it is doing the adjustment for you. So you are not training the parameters or the weights. So you're not adjusting the parameters or the weights of the neural net. The neural net is doing it itself. Then what are you controlling? There are other parameters that you control, or basically uh, they are called hyperparameters, and that would be the, say, the loss function, the activation function, and there's a concept called learning rate that comes, like how much are you going to adjust, right? That is in the next slide while we understand back propagation. But these are certain things that you try to adjust, and instead of the actual parameters or the weights, you adjust the hyperparameters or the functions that indirectly affect the actual parameters. So now we have two layers. One is the weights or the actual parameters on which the prediction is happening, and the other is the functions and the values that affect those corrections, right? And what are those corrections? So basically, what this is the basic example. What we are using is the chain rule in derivatives. So we calculate the derivative of the error with respect to a certain weight, right? And say it is we have 10 hidden layers, and I want to calculate the derivative of the output from one of the weights in the fifth hidden layer. So how would I go from fifth from output to the fifth? That would be through the chain rule. uh, and the concept is basically similar. What it does, so this is the total error, which can be your MSC, right? You you calculate a derivative and keep the a value of the output function as constant. Then you calculate the derivative where you uh, differentiate the output function based on the input value, or this particular equation, right? You keep the value of y, this particular equation as your variable, and you differentiate this particular function to get the derivative. And then at the end you differentiate this particular value. This is right now it looks like the equation of line, and if you differentiate it, you'll get the derivative will be w, right? But as I said, for RNNs and for other networks, it can be a different function as well. Even though like even in matrix calculations, you can have squared of a matrix and all that, right? So that would affect your the differentiation process. But this is the basic idea. So this way you got the derivative of the uh, s- uh, say you got the derivative for this the correction point for this particular weight, right? Now this particular weight is the output for this hidden layer. So again, if you apply the same process, this would become your new error, and you can start differentiating this particular functions, whatever activation function was there, and whatever input function you have used, and you can come up with the value of this particular weight. So that way you can go back and back and back, and treating each and every weight as the error for the previous node. You can come up with the corrections in the previous layers weights, and you can trace back to the input layer. So this is the basic concept. uh, I hope it's clear. Like, obviously, I here I've chosen sigmoid, but you can have all sorts of activation functions, and uh, based on the activation function, the derivative would change, but all that is computed internally. And there are obviously for that is because they have certain optimizations where you don't calculate the derivative of that function again and again. You already have a preset value and you quickly apply it. But if you want to do it by hand, or if you have a activation function that is not common, you'll have to go through this whole process to implement it. But that is basically a research thing. For what you need to know is that internally it already has uh, matrices for these calculations, and it just applies those operations and it quickly comes up with the answer. And that is why it is fast, because you can imagine it has to go through a lot of features at a single time, and it has to give you answers within a few milliseconds, right? So a lot of optimization and heavy computation goes into it. Now, last time we discussed max pooling, right? So this is something specific to uh, images, and because that is where most of the matrix calculation is. But the concept of max pooling can be applied for computer to understand how filters are applied on images, and other different operations are applied on them, like conf 2D. How does the function conf 2D work internally, right? And how does max pooling work? So like I said last time, you have a given image or a matrix, and you have a kernel. So you define the size of the size of the matrix that you want to operate on, that you want to operate with, not on, right? And this can be convolution. This is the convolution operation, but this can be like max pooling. You can use it to derive the derivatives. You can use it for also you can use it for masking, like we talked about erosion and dilation last time. All of them would follow the same concept. What is the concept? I think this you must be studying this image and you must have had a little idea, but we'll go through the calculations. So I selected a 2 cross 2 matrix and I started applying it on this image. What it does is it goes in sections of 2 cross 2. It looks at these values. It says, okay, this is the max value, and it will take 10 and put it in the output variable. Then it will go here, it will look for the max value and put it in the new matrix. Then it will go here and it will say the max value is 3, and it will put it in the uh, new matrix. Now here what you see, this is called padding. So if the image and size and the kernel size don't overlap, what it will do is it will assume 0 0 as values, and it will complete its operation. It If you don't do padding, it will ignore 3 and 1, or it will give an error depending on the implementation of the library, right? But padding is one way to include all the data, right? And then the way it is moving is called step size. So in matrix calculation, this is also very important. Here the default step size is 2. What will happen if we take the step size as 1? Then first it will select from 10 1 10 9 1 3. Then it will select from 1 3 2 8. Then it will select from 2 8 4 6. Then 4 6 3 1. What if we make step size as instead of 2 as 3? Then it will first select from this box, then it will select from this box. It will leave these two values. So this is why step size is important. And again, step size becomes one of your hyperparameters, and it becomes a topic of debate when you are trying to implement new matrix calculations. But for max pooling, it is standard. You in max max pooling, you don't overlap or leave values. The step size is the same as the kernel size. Now, and step size also means the if it's moving in say uh, in the x axis, not the x axis, if it's moving in the right direction, then it will go down 2 steps as well. So instead of starting from 9 3, it will start from 5 7, and it will do the same operation. It will grab that particular subsection of the image, and it will look for the max value and take it there. Now, as I think I've mentioned it last time, but I'll mention it again. Why are we taking the max values? Because the image itself is very big, and we are looking for important features. So once we apply the convolution matrix, what we do, we generally apply max pooling to extract the most important variables. And in images, the most important variables are the ones with the highest intensity, because now it's not the intensity of the pixel, it has been operated on, and now it has become a feature, internal feature, right? And what is like, if you apply convolution operation on an image, what would be the output? The output would be similar to uh, applying edge detection on the image. Okay, but as you go forward, it would become less and less intuitive, because here also you are increasing the number of dimensions, just like in SVM. So the size of the curve of dimensionality will be at work, and the size of your features will keep increasing, because now by feeding 100 x 100 image, you have, and by having say 10 hidden layers, you have increased your data set size or the parameter size 10 times. And that is why max pooling also helps, because it helps you reduce the number of features and extract only the important ones. But still, we are applying a 2x2 or a 3x3 kernel, so the size of the feature set will not decrease a lot, but it still helps. But again, ultimately, you have a data set that you have a feature set that is like uh, 2 or 3 or 5, depending on your architecture, that is the 2 or 3 or 5 times the input variable, right? So that is why a lot of times in image processing, they choose the size of the image as 100 cross 100 or 300 cross 300. Rarely will they work on an image that with a resolution of 1000 cross 2000. They, because of the compute issues. Okay, and again, this is max pooling. There are other operations like global average pooling and average pooling, and convolution, and a lot of other operations that we can apply, right? Which all work on the same concept of matrix, of this convolution operation. Okay, the convolution matrix and the convolution operation are both different. Okay, uh, the what's main is the convolution operation. The convolution matrix is nothing but a set of random values, and I'll send you a link to how those random values are selected. Like, there are different techniques. Even all the functions that generate your random values are not purely random. They are based on certain algorithms that help you generate partially random values. Okay, this might seem weird, but in nature, in computers, there's nothing called purely random. If like, if you have used the random package, you might have seen they select a particular seed value, and if you select the same seed value, you will get the same output. Yeah, it seems a little counterintuitive, but that's how it is. And one of the ways is to generate these random values with a fixed seed. Why is it important to fix the seed if we want randomness? Because if we do not select a certain uh, starting point, it will be very difficult for us to reproduce what we are doing. Like, okay, you train a model, you get good results, you train it again, you start getting different results, and now you can't figure out how you got the good results. Okay, so that is because internally it is every time it starts training, it picks up certain random values. And if you want your results to be reproducible, if you want other people to like to be able to do what you are doing, you need to select a seed value for those random initializations. But through research, people came up with better solutions. The most popular one is Xavier initialization. I'll send you a link to that paper. If you are interested in research papers, you can go through it. But if you're not, then just know that within the documentation of whatever library you are using, there should be an option of initialization, and it should at minimum have two options. One is random and second is Xavier. Okay, so this is how so those random values are used with the to convolute with the image, and then it goes to the output, it calculates the error, it back propagates, and it starts correcting those random values. And with each and every pass, those random values start moving in a certain direction and start becoming more and more useful for us. So this is the whole process. Now, whatever I have explained you through images is completely valid through other methods as well, because instead of an image, you can directly input any other feature as well. And how would we feed an image? So a lot of times you'll see we use a flatten function to convert that image to a 1 cross n matrix and then feed it to this neural network. Or some but internally you it's still doing the convolution operations, it's still doing the same thing. So a better way to visualize it would be like this. And even at the output section, you if you have went through the notebook, and I hope you got the link, you would if not, just I can share it again here for people who have missed it. uh, if you go through that particular notebook, you'll see there is a flatten function within the Keras library, which is used before the output layer. Because ultimately, if you are trying to calculate the output, and if you are using the sigmoid function, and if you are using this particular line calculation for calculating your output, then you need to have, instead of matrix, you need them flattened. So as far as I remember, in Keras you don't need to flatten it uh, at the input now. I think in some older version you needed to do that, but ultimately at the output layer you still need to flatten it to get the final yes or no, or whatever classification or regression problem that you are trying to solve. Okay, and this is the basic calculation of a neural network. Obviously you can I'll share you four things. One is the exact an article that would take you through the exact calculations of back propagation if you are interested in doing them by hand. If you just want to, even if you just want to understand them, you can you can not go through the calculations, but look at the calculations and the concept. It's a very good article. The second link I'll be sharing will be for Xavier initialization, so that you know, so that you get a little bit idea of how hyperparameters, because this is also again a hyperparameter. Like, at what point are you starting? Because uh, because the starting point, choosing a starting point becomes important. If say you because say you have a hypothetical ideal value for each and every weight. Say you have 1 million weights, and each and every weight has its ideal point, right? So where you are starting becomes important, because if you start off, say, uh, at a very at very far away from the ideal point, right, for say even half of those values, because of because randomness, right? So the random, according to randomness, there is a 50% probability that you are far away, and there is a 50% probability that you are close to the actual value. Even though that is an idealistic situation, practically, uh, you would most probably be very far away from the ideal value, because there are like infinite set of values that can be there, right, for the right answer, right? You don't know where to start with. So if you start off at the wrong point, it would take more computation, more time, to reach the right answer, right? And all these functions that I showed you, all these activation functions and loss, mainly loss functions, they have a certain characteristic, that they are con- convex functions. They are what is called a convex functions. So if you try to plot them out, you'll find that there is a single maxima or minima point. Because if you are starting off randomly, you don't want to get stuck at a minima, that like if there are two minimas, one is the and one has higher value, right? Then you don't want to get stuck at the minima with the lower value. And that is also why, but like if there are certain situations where you have non-linear functions, and you have, and your loss function and everything is not always convex, right? And what do I mean by convex? Like, just imagine a function which would plot out as a bowl in real life, something like that. So it will have a lowest point, right? And in there you can start anywhere, and you would reach the lowest point. That would be your ideal point. By lowest point, I mean the ideal point, where where the loss would be minimum. So all this back propagation that we are talking about, what it's doing is, it's trying to move to a point where the error is minimum, and it would move the weights in a direction that would minimize that error. So which would be your ideal value of the weight, and lower the error, the closer you are to uh, strong correct predictions, strong predictions, right? So there's a lot of math revolving around how to choose your loss functions and activation functions. Loss functions are mostly concerned with convex functions and starting points and everything, and activation function is more about how, whether the hidden layers like are becoming redundant or not. Because if you have like say you have 100 hidden layers, there might come a point where uh, the value at the 99th layer becomes too big or too small, or it stops changing, something like that, right? Not stop changing, like like it might happen that during back propagation, the amount of change, if you have 100 hidden layers, the amount of change to the first or second or third layer is negligible, and it's not moving to its optimal point at a speed that we want. Okay, so that is why initialization becomes important. And the second thing that becomes important is what we call the learning rate. So here in this example, we calculate a total correction, right? But a lot of time what happens is that we don't want to directly go to that point. We want to approach it slowly and slowly. So this is what a learn where the concept of learning rate comes in. Why do we want to approach it slowly? Because this calculation will not give us the right answer in one go. It will only give us the direction in which to move, whether to increase the weight or decrease the weight. So we use learning rate is nothing but the value with which you reduce the correction. So it can be 0.0001 or whatever, and you might say okay you need to correct by 1,000, and in second pass it might say okay you need to correct by 100. So if you're moving 1,000 steps at a time, you will never be able to move 100 steps, right? So your so your movement has to be small, but not too small, otherwise you'll again the computation time will increase. So these are all the, so the learning rate, the random initialization, the activation function, and the loss functions, these are our hyperparameters now. So, and there are a lot more. I'll not keep these are the main one, that's why I introduced them. But if you go into details, there are a lot more things that you can control. But activation function and is very important with back propagation, and initialization values are very important if you want the loss to converge to the minimum value. And the resources I was talking about, the second paper is that's why related to Xavier initialization, and it will talk about learning rate and everything. So you can go through that as well. The second two papers will be related to RNNs, and you can go through them if you want to understand uh, a, a little more complicated neural networks. Again, it will work on the basics that we have discussed right now, but it will keep introducing new concepts and new calculations, and it will keep modifying the basics. But this perceptron is the basic unit, and you will find these calculations everywhere. Okay, and again I'll check through the questions. They're not stages, classification and then voting. No, there is bagging and then voting. And so no, there is bagging includes voting. So there is random sampling and then voting. So the random sampling happens for the feature set, right? Like if you have a table of say 10 columns and 1,000 rows, it was, and you have defined okay only want the top 6 features, then it will randomly select 6 features, and it will randomly select say 2 out of 1,000, say 500 data points, and it will try to create a decision tree. And once it has all those the first stage is the first process is related to selecting the input. Then whatever process of decision tree is creating a decision trees that it will follow. Once all your decision trees are calculated, then it will have a second step, which is voting. Okay, if you give it say a value, what will the decision trees say? You, if you have 10 decision trees, what will all of them say? And if say like 9 decision trees say yes, or whatever you're trying to predict, like dog or cat, or yes or no, generally yes or no, then it will say okay, go for a yes. Now in regression, max voting won't work. In that, you'll have to average the values out, or you can use any other solution as well, but averaging is one of the most common and intuitive one. I hope that answers. So classification and regression are different, and the stages of random forest are different, and they're not stages, they are just like techniques around the decision tree to make it more robust. So these are the two modifications to decision trees. Okay. uh, in an activation function in hidden layer or output layer. So you can have activation function in hidden layer as well and output layer as well. Like we discussed last time, in hidden layers we generally prefer leaky relu, and in output layer we generally prefer sigmoid or softmax. And then the output of the sigmoid or softmax is used for error calculation or the loss function. I hope that's clear. BPM. Where is the calculation of error again? Output layer, right? Then some hyperparameter. Yeah. So that I think what you're trying to ask is how the weights are affected, and this is what we discussed in the back propagation function. So the error the error will basically affect the weights, and not weights of features. Weights are basically the features. I hope that's clear. So where is the calculation of error again? So in this particular node, it will have all the inputs. It will calculate this using this equation of line. It will apply the activation function, and then it will apply the loss function at the output layer. Say sigmoid function gave an output of 0.99, and you wanted a 1, so there's still a difference of 0.01. So that would be included in this, say it would be in this loss function. uh, no, this loss function is for regression and this one is for classification, right? And after calculating the error, it would propagate that value back to the weights and make corrections again. uh, I hope it's answered. Live audience. Any other questions? What is basically the class 1 and class 2 in the random forest? That you have to decide. That depends on your project. Like I can give you a different example. Okay. Say uh, say you are in a you are a you work in a supermarket, and you have a certain event coming up, and you want to judge what would be the most purchased item during that particular sale. So you can have all the products will become your class, right? And their purchase history will become your input features, right? So that way, if you want to say if you want to predict the weather, and you have rainy and sunny and cloudy, then that would be your class 1, 2, and 3. Okay. Okay. Any other questions? Because this is the max I'll go for this session. I won't get you into more mathematics. And I'll start sharing the links as well in the chat. So these are some good research papers. Again, if you're not interested in the research, if you're just interested in the programming part, then this should give you a good idea of what's happening under the hood, and you can just go through the documentations of whatever package you are using. I would recommend Keras or TensorFlow. TensorFlow is a little difficult, but Okay, so the chat section is restricted. I'll put it in the QA section. Okay. Any other questions, people? Okay. Okay, the questions might not be visible to everyone. Someone is asking for attendance. Yes, the section is closed. Like, if you don't have any other questions, that is. Uh, Rag, I don't see any other questions. Just please check once.
Yeah, I also don't see any more questions.
Yeah, I think like I think people need some time to digest that, because even though it looks simple, it's there are a lot of components. So even if you have some questions later, you can just send them over uh, via Surag, or you can reach out directly to me.
The question, if you are answering to that live, if you click on three dots at
Yeah,
the
I am marking
uh,
them as answered as live, but there are
uh,
certain questions that are like attendance form and all, so I have left them for you. Yeah. Okay. So what are the four links? So these are the three links. First one is for hyperparameter initialization, the Xavier one. The second one is to understand recursive neural networks. So that mathematics gets a little more complicated, and it requires a little more visualization. So you might want to go through some other articles and get yourself completely familiar with feed forward neural networks if you want. And or maybe it's a very good article, paper, uh, educational paper, it's not a research paper, it's an educational paper, so you can go through that. And the last one is attention is all you need, a highly recommended paper if you want to understand big models like ChatGPT. Again, it is the last paper, attention is all you need, is maths heavy. uh, it might You will obviously need more than months to go to understand it properly. And if you're a beginner, like a complete beginner, and if you're just trying to understand back propagation and all, then uh, it will take much more time, but still highly recommended, because this is where we are currently. Like, all those calculations have become more and more common and are being used for bigger uh, natural language understanding models. So for natural language understanding models, the basic concept remains the same. The only but you need to understand RNNs to start uh, natural language understanding models in neural networks. So that is a little more advanced, and that's why I've skipped that for this session. Okay. Okay. Certification related questions. Okay. Hmm. Okay. Fairly good questions, but no more questions. Okay. RL related. R RL. Can you please give the full form? Are you recursive learning? Are you talking about RNNs, or is it like any other technique that you're talking about? Like, there are a lot of techniques we haven't touched upon, I guess. supervised and unsupervised parts. I've mostly touched on supervised part. Okay, because unsupervised is not that common. There is not a lot of research on that. So the basic idea is that supervised is something that you where you feed it the data and you give it the answer as well, like, and it would try to understand how how to use those inputs to get to that output. In unsupervised, you don't even give it the answer, and it has to figure things out itself. So that is quite unpopular, and it is used to get the basic understanding of the initial data set. The supervised, I didn't touch upon that, but this is like the basic concept. Reinforcement learning. So RNNs I've already shared a paper. So that would be the second paper. uh, if you go through it, it's written by like people from DeepMind and everything. So there are a lot of papers. What I would suggest is go through the first paper that introduced that idea, and through maybe a educational paper or a survey paper that talks about the improvements that have happened. That would be the quickest way to ramp up on what's currently happening. And then you can because if you go through a lot of random papers, what will end up happening is you'll learn about calculations that are not relevant anymore. And until and unless you're doing a PhD or something, it will be a waste of your time, right? So just go through the initial reinforcement learning paper, go through the some survey papers or the one that I have shared, and then look for the latest research that's happening. And ultimately, you'll have to get a little bit into the research papers because that's where all the new techniques come from. There is still no like formal like channel through which all these things comes. You have to keep a track of like what Google is doing, what Facebook is doing, and what type of research papers they have released. Okay, so sorry. uh, I think RNN is recurrent neural networks reinforcement. I think there's just a minute. I think I'm mixed up two concepts. Okay. Yeah, I think I mixed up two concepts. No, it's reinforcement learning only, na? If you go to the title of the page. Yeah. Yeah. I think Surag, we're done with questions and everything.
Okay, that's because somebody summarized everything. Okay. So yeah, I think we are done with the question. If there is anything that pops up in your mind afterwards, please do come into the community and ask the question there, and or you can forward the question to me. I will forward it to Vibor, and I will post it in the community about the answer. So yeah, with
Yeah,
that,
just one point. Someone has summarized it, but in their point, it's a good summary actually. But in their point four, the perceptron node will pass through pooling process. That is not always true. The pooling and that the pooling layer is a different layer. The perceptron will pass through the activation layer, and the loss function is at the output layer, which is at the very end of the network. Like just like in this uh, uh, process, right? The output layer is the one that has the loss function after the activation function. So all these nodes will have a perceptron and a activation, but only the output layer will have a added loss function, and pooling process is a hidden layer in itself. The output layer will be the result. Yes, all the other parts are like good. So others might want to refer to this answer. Yeah. Thanks, Surag. Thanks, and sorry for interrupting you.
No worries, no worries. Uh, there is one more question, I guess. Was it? Okay, no, it's not a space question. Okay. Um, yeah, that's it for the day three of the AML Study Jam, and I hope you guys have enjoyed and didn't face any issue during the session. And and I have also shared the attendance form for today. Please to fill it out, and on the day four, you will get the attendance and the certificate for the all four Study Jam. And yeah, be sure to be on the last day as well. And the meeting will be held in the same, and because it's a recurring, and we'll have it the same one. And you can come back to the same meeting where you don't need to fill up the form or which you had to fill up before you joined to the session. And please make sure you join the community. And I have shared the link before as well. There is some people who are not in the community, and that will make you kind of uh, in in terms of you're not able to get the updates, you're not getting the updates on time. So be sure to be in the community so you'll get the update, and we'll have more session coming up and the hackathon which will be happening after the study jam. Okay, with that, we are done here, and I want to thank you, Vibhor, for taking his time to share his knowledge with everybody here. And thank you all for taking your time to be here and learn something new with us. And be sure to be in the community, and happy learning. With that, we are concluding the day three and looking forward to the day four. And have a great Saturday.